Dispersion of white light by a glass prism. You must have seen and appreciated the spectacular colors in a rainbow. How could the white light of the sun give us various colors of the rainbow? Before we take up this question, we shall first go back to the refraction of light through a prism. The inclined refraction surfaces of a glass prism show exciting phenomenon. Let us find it out through an activity. If a prism is placed in a room and a narrow beam of white light is allowed to fall on one of its refracting faces, what do you observe? It is found that light coming out from the other face of the prism is split to 7 colors. What are the 7 colors that you see on the screen? The various colors seen are violet, indigo, blue, green, yellow, orange and red. This phenomenon, the splitting of light into its component colors, is called dispersion of light. The band of the colored components of a light beam is called its spectrum. Why does this happen? The acronym WIBGY will help us to remember the sequence of colors. We have seen that white light is dispersed into its 7 color components by prism. Why do we get these colors? Different colors of light bend through different angles with respect to the incident ray as they pass through a prism. The red light bends the least, while the violet the most. Thus, the rays of each color emerge along different paths and thus become distinct. It is the band of distinct colors that we see in a spectrum. Isaac Newton was the first to use a glass prism to obtain the spectrum of sunlight. He tried to split the colors of the spectrum of white light further by using another similar prism. However, he could not get any more colors. He then placed the second identical prism in an inverted position with respect to the first prism. This allowed all the colors of the spectrum to pass through the second prism. He found a beam of white light merging from the other side of the second prism. This observation gave Newton the idea that the sunlight is made up of 7 colors. Any light that gives a spectrum similar to that of sunlight is often referred to as white light. A rainbow is a natural spectrum appearing in the sky after a rain shower. It is caused by dispersion of sunlight by tiny water droplets present in the atmosphere. A rainbow is always formed in a direction opposite to that of the sun. The water droplets act like small prisms.
What we see as light is only a small part of the electromagnetic spectrum. The electromagnetic spectrum refers to the many types of radiation released from stars, including our own sun. Electromagnetic radiation travels in waves. Frequency describes how many waves per second a wavelength produces. Wavelength measures the length of an individual wave in meters. Scientists describe the electromagnetic spectrum as a long line. At one end lie radio waves, with the longest wavelengths and lowest frequencies in the spectrum. A single radio wave has the length of a football field. After radio waves come microwaves, which produce more energy due to shorter wavelengths and higher frequencies. Cell phones, radar, and microwave ovens use microwaves. Next comes infrared light. The sun, fire, living creatures, and other heat sources all produce infrared light. While we cannot see infrared light, we feel it as heat. Visible light occupies a narrow slice of the electromagnetic spectrum, nestled between infrared and ultraviolet light. Red wavelengths have the lowest frequencies and longest wavelengths of visible light. As you move from red through orange, yellow, green, blue, and finally violet, wavelengths shorten and frequencies increase. From visible violet light, we move into ultraviolet frequencies. Human skin produces vitamin D when exposed to ultraviolet light, but excessive ultraviolet light causes sunburns. Next, X-rays, which pass through soft tissue but not denser materials such as bone, making them valuable for medical tests. X-rays also have security applications such as airport baggage checks. Gamma rays produce even shorter wavelengths, higher frequencies, and more energy. In comparison to the football field-sized wavelengths of radio waves, gamma ray wavelengths are as small as atom nuclei.
In this episode, we'll be taking a look at the electromagnetic spectrum. Our goal is to understand what energy is and why it's so important in the study of astronomy. If you look back at the history of astronomy, arguably the most important moment came in the early 1600s, when astronomer and mathematician Galileo Galilei first improved upon the telescope and used it to look at the heavens above. Galileo noted all sorts of interesting observations that had never been seen before, including the fact that the planet Venus appeared to go through phases, just like the moon. He also noted that the planet Jupiter had several moons of its own. In addition, Galileo was the first to see that there were actually spots on the surface of the sun that moved as days went by. Telescopes have improved quite a bit throughout history. They've grown larger and more powerful. Modern observatories today have massive telescopes with huge glass lenses that allow us to peer to the depths of the universe. We even have a major telescope that's currently orbiting the Earth, which is able to see the very beginning of the universe. But we'll talk more about that later on. So why is it that these telescopes are just so important to our understanding of the universe? What is it that a telescope does? Well, it's pretty simple actually. Telescopes collect light. When we point a telescope up at the sky, no matter how large or small it may be, what it's doing is collecting light that's flying throughout space. It's amazing how much we can learn about the universe just by studying this light. In fact, that's actually what astronomy is. It ends up being the study of all of the light flying around in the universe. It's amazing what we can gain by studying this light. But this brings up another question. What exactly is light then? Well, that also can be answered with a simple response. Light is energy. But again, this leads us to yet another misunderstanding. What exactly is energy? Well, if you look it up in the dictionary, energy is defined as the ability to do work, the ability to have an impact on something. What makes it such a tricky concept, though, is that there's many different kinds of energy that are very unique and very different from each other. Energy includes mechanical energy, thermal energy, electrical energy, nuclear energy, light, and heat, amongst others. And all of it can be actively working in the form of kinetic energy, or it could be stored up for future use in the form of potential energy. It turns out that in the study of astronomy, the most important type of energy is light and heat. And this is shown in its different types on a diagram known as the electromagnetic spectrum. Let's take a look at a short video from NASA which explains what the electromagnetic spectrum is and how exactly it works.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our Sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
So the electromagnetic spectrum includes all the types of energy flying around in the air on Earth and in the universe. What you should have noticed from the video is that there's a variety of kinds of energy on the electromagnetic spectrum. They're all different from each other based on the fact that they have a different wavelength, and that's a key idea. Fortunately for us, on page 14 of the Earth Science Reference Tables, we have a chart summarizing the types of energy found on the electromagnetic spectrum. It's a very simple chart that lists the different types of energy and whether or not they have shorter or longer wavelengths. Let's take a look. What you'll notice is that on the far left of the chart, we have the shorter wavelength energy. And you might remember from the video, this is more energetic, and therefore this is more harmful to living things. The shortest of all wavelength energy is called a gamma ray. Then we have X-rays, Yes, these are the same kind that you would get when you go to the dentist or the doctor to check if you have a broken bone. It's a strong type of short wavelength energy. Then we have ultraviolet energy. And these three are generally considered the short wavelength types of energy. On the right side of the chart, we have longer wavelength energy, including infrared, which we feel as heat, microwave radiation, and radio waves. Microwaves are what allow your cell phones to communicate with each other, while radio waves transport, you guessed it, radio signals. Now, out of all of this energy flying around, there's a very, very small band of wavelengths which humans can actually detect with their eyes, and that is called the visible light energy, or the visible light portion of the electromagnetic spectrum, seen here in the center. What you'll notice is it's a very small portion of the entire spectrum, and what that means is that of all of the energy flying around on Earth and in space, we can only detect a very small bit of it with our eyes. But what we can detect, we can distinguish as the colors of the rainbow. What you notice on the chart is that visible energy is broken down into the 6 colors of the rainbow, with the shortest wavelength on the left-hand side being the color violet. Next to violet with a longer wavelength is blue, then green, yellow, longer still would be orange, and the longest wavelength color is red. So those are the colors that make up the rainbow, and this is what allows us to detect colors in the universe and on Earth around us. What I'd also like to point out is that next to the color red on the chart is the next type of energy, which appropriately is called infrared. And again, we can't see infrared, though we can detect it as heat. Similarly, on the left side of the visible light spectrum, where the color violet is, next to that would be found ultraviolet. This too we cannot detect, though it is flying around in the Earth, emitted by the sun. Ultraviolet is the type of energy that gives us a sunburn when we go outside in the sun for too long. The sun does emit primarily these 3 types of energy: ultraviolet, visible light, and infrared, with the majority of it falling in the visible light spectrum. This is fortunate for us because we don't want too many gamma rays or X-rays floating around, as they can harm living things. So let's imagine we took a telescope and pointed it at the sun, and collected light from the sun and sent it through a fancy machine called a spectrometer. What we would end up with is a crazy looking image like this. This is the visible spectrum of the sun. And what you notice is that the visible spectrum reflects all the colors of the visible light, essentially the rainbow. But what I also want to point out are these strange looking black lines. Think of these as the fingerprints of the different elements making up the sun. For example, the sun is largely made of the element hydrogen, and so within these black lines is the fingerprint of the element hydrogen. Why is this important? Well, it allows us to determine the elements that make up a star or a galaxy by just looking at the light given off from that star or galaxy. It's amazing what we can learn by looking at energy. We can learn how hot and therefore how large an object is. We can learn what elements it's made of. More importantly, though, we can use these spectra to determine if an object is moving. We can tell if something is moving towards us or away from us. And that would set the stage for one of the most important theories in the history of astronomy, the Big Bang Theory. That's what we'll be talking about in the coming days. Thanks for listening.